morning, everyone. My name is David Palchak. I'm from the National Renewable Energy Lab in Golden, Colorado. And some of you have maybe seen me this week talk about some of our bulk system power planning work. Today I'm going to talk a little bit about what we've been doing with distribution companies around the country, in particular one here in Delhi with the utility BRPL. We're going through a process with them to help them really understand how distributed energy resources might impact their system. And I think this is a really important topic for utilities right now as rooftop PVs grow, the potential for storage to come online, and other technologies that might be new, and something that is potentially hard to plan for, given that there are a lot of unknowns. And also, was there another presentation on here? I think maybe this. Okay. Apologies for. Was there another folder? I dragged a presentation on here this morning. Yes. No, that's not it. No. There was another folder that was open in here. Sorry, everyone. No. Here, let me look. Okay. Apologies for that. So as you can see, we're working on this in partnership with BSES, BRPL. They service a lot of the Delhi area. And as you can see, I am toward the end of this author list, and I apologize that that the leaders of this work weren't able to be here. But I do have an email at the end of this in case I miss any questions. And as I said, a little bit outside of my expertise, so apologies for anything I might say that's outside of kind of the technical distribution planning area. So I'm going to go into some of the nitty-gritty of actually modeling distribution feeders in India and some of the challenges that we found, and hopefully this could be useful for researchers in the future. I'm going to talk through some very detailed pieces of building a model and data cleaning, but ultimately, hopefully this is something that would be open source, and as we try to make our work out there for everybody to use in the future. So I'll talk about building the model. I'll talk a little bit about how we're thinking about EVs in the hopes that we can improve the data in the future and build that improvement into our EV modeling. Also looking at battery energy storage systems, how we're thinking about sizing, how BSES has directed us to think about sizing and how they're thinking about it now, and how we would use that for peak shaving. And then looking a little bit at the simulation architecture. That part's a little boring. Ultimately, it's us doing as many scenarios as possible with a big computer. But I think that's important from the perspective of having really robust answers. And I'll talk a little bit about our plans. So the challenges of distribution planning come from essentially the different sources of data and how those are often incomplete, especially in India. And so we had a number of different techniques to try and close the gaps on some of those data issues, making sure that we validated our model based on different measured pieces of data, different pieces of metering where we could measure at one point and use some average values at a different point to close the gap on getting full time series data for the analysis. And ultimately, what we found at NREL is that modeling the primary network is not sufficient for looking at some of these questions of distributed energy resources and getting down to the secondaries and looking even at the building level and trying to understand what could be voltage issues, other stability issues that you could see very far down on the feeders. So here are the steps, as you see in the diagram on your right. As you can see, we're modeling in OpenDSS. This is an open source network modeling framework, and we're importing GIS-based data. And usually utilities will use this for some visibility over their network. And so oftentimes this is the data that's available, but we need to turn this into a usable model, and that requires a number of steps, and I won't go through them all, but essentially the GIS data will have a lot of gaps when you try to explode that into an actual model, and it takes a lot of validation of the modeling to make sure that all of the lines are connected and all the feeders, or the distribution transformers and all the components on the feeder are represented correctly. So as you can see on the diagram on the bottom, and so on the top we have the GIS model that we actually get. Not a lot of detail there, but as I said, we're trying to model down to the building level. And what we do in the US, and we don't have a picture of that here, but oftentimes we'll use something as simple as Google Maps and map the primaries and then use Google Maps to actually attach all the secondaries and all the houses and buildings onto our models to make sure we're capturing the reality of what's going to happen farther down the line. So something that's important in our model is we're actually doing time series analysis, and that requires a lot of good data, which is not always available, giving missing links on meter data, on distribution transformers. And so the way we were filling that is using average loading profiles to essentially create some synthetic data based on average monthly profiles. And this is a little forward thinking from where the modeling might be at most Indian utilities right now in doing actual time series analysis and trying to model multiple years. But for us, it's very important to make sure we can forecast into the future with full time series complete data. And so what you're seeing here is just the monthly average profiles, utilizing those to make sure we can fill in the actual hourly data on the bottom with some idea of what it's going to look like from a seasonal perspective. Load allocation is an important topic when you're trying to model secondaries because there's not data down to this level typically. And what we ended up doing was developing an evolutionary algorithm we were essentially validating our model based on monthly billing data from customers and DT measured data for power and voltage, which was spotty in some cases. What you see at the bottom is the results of the algorithm with the initial voltages based on missing data and running an OpenDSS model from those initial voltages. And ultimately trying to converge with our target voltages based on the measured data down to the customer. And so we're essentially trying to fill the gaps in all of the components that are along the distribution line that we don't know about, all the capacitance within that distribution line, and making sure that we're understanding, filling the gaps with what's happening at the DT level, what's happening at the feeder head, and filling that with these different algorithms to complete and make sure our model is complete in terms of capturing the voltage, because voltage is ultimately some of the issues, one of the main issues that we're looking at when we put EVs and PV rooftop on the system. So our EV demand modeling is somewhat simple at this point, but we did try to capture some of the trends that we expect to see. So what we did is we modeled, right now we're modeling just 2 feeders, in the BRPL territory. And as a transmission person, I was thinking that can't be that hard, just 2 feeders. But I was quite wrong. So it seems that every feeder is different, and so while we're only doing a small segment and getting a small glimpse into what BRPL might do, building up these networks is really important. EV modeling is a concern that these distribution companies have as India's charging ahead and trying to get EVs on the system, and they're trying to understand what's going to happen to our feeders if residents' public charging stations come up. So we came up with some simple algorithms, adding EVs. What we have here is about 2,000 EVs on the system. We randomly located this along the feeder, both did residential slow charging as well as public charging stations, and estimated when these EVs would be charging and what their initial state of charge would be, given that certain times of the day they're going to arrive at an EV charging station and they're maybe going to have some charge left in their battery, and making sure that we understand what the full load would be is an important part of this. What you see at the bottom is essentially taken from some of the knowledge of what EV demand charging is going to look like in the future, where there will be some charging in the middle of the day at workplaces, but mostly people are going to go home and charge in the evenings, and so that has the potential to really impact evening loads. So as I said, we had about 2,000 EVs that we considered that added up to about 1 megawatt of load during some periods of the day. And the bottom 2 plots are showing, from our baseline model, what the voltage profile looks like throughout the day on a per unit basis. And as you can see from the bottom plot, during the evening, you see the voltage profile drop quite a bit. And so this is something that will be good for distribution utilities to understand if there are large charging stations potentially coming along their feeders, and giving them some visibility of how that's going to impact things, and give them some signals of upgrades that they might need to be making if this turns into a problem. The sizing of the batteries was a conversation that we had with BRPL many times, and trying to think about this question of sizing batteries for different things. And ultimately what we ended up coming around to is that distribution transformer deferrals were the biggest thing that they could wrap their head around as far as the potential for batteries to offset that upgrade. So this graph is a little bit complicated, but I'll try and explain it if I can get a mouse here. So what you see here on these blue points are actually real data points from distribution transformer loading. So on the left axis we have the energy, and here we have the peak. And so all these blue points are actually measured data of transformer loading. And I lose my mouse. Along this blue line is actually what we see as a 4-to-1 ratio battery. So as you can see, from peak to energy ratio. And we chose that because it seems to be the most commercially available battery that's going to be available. And obviously, once you start thinking about all the different ratios, it gets very complicated to try and analyze what sorts of batteries we would have. When you look at that purple line, that is a battery that would take care of all of these overloading conditions. And that would be a very expensive battery to buy. That would be a 300 kilowatt battery, and it would potentially defer any need for transformer upgrades in the future. But that's probably not the most cost-effective way to think. And so we just came up with some rules of thumb with BRPL, where if we could take care of 70% of the overloading, that might be the right place to look, where we still have overloading conditions, but we don't need to necessarily take care of all of them. And so ideally, this would be something that you would actually try and optimize from a cost-effective standpoint. But given that batteries are still very expensive, coming up with these frameworks for thinking about not trying to buy batteries that would take care of all overloading conditions might be a good step. So that's what you see on this green point, where, okay, thanks. Where you have a battery that will take care of 70% of the overloading conditions, but also be much smaller in size, almost half the size, just to take care of most of the overloading conditions. I'm going to go ahead and skip this. This is just a simple graph that shows how this would work. The utility would ultimately have control of the battery, and they would be able to trigger it or set it up to be triggered during different loading points. So actually running the model, looking at the transformer power here in the top graph, you see the base case where we have overloading conditions outside of the red lines and the blue line there. And then when we use the battery, we're able to shave the peak and keep it between the blue lines for most of the time. There's certainly still a little bit of overloading, but given that we size the battery at almost half, there's a lot of energy savings and actually taking care of a lot of the conditions here. And the bottom graphs are just showing what the battery is doing throughout this, and you can see the peak in the bottom right where the battery is maximizing the power output to take care of that largest power peak in the middle of the day. As I said, we've got a big computer. We like to use it. I guess this is partly to brag, but also to say that scenario modeling, as I do with my transmission scenarios, I think it's really important, and it's really important to try and think hard about what you're going to model. As you can sort of see in these blue lines, these are a number of our scenarios, and thinking about 70% loading, peak shaving, having different EV modeling scenarios, and putting all of those together to come up with robust answers is a really important part of doing this sort of research, especially at these early stages as utilities are starting to think about this. So to conclude, ultimately at NREL, we've kind of stopped just modeling primary networks when we're thinking about distributed energy resources. Secondaries are really important, and there are tools, and even using something simple as Google Maps can really help build out those network models. Developing reproducible methods, I think, is really important, at least from our perspective. We're hoping to take this to many utilities around the country and keep it open if we can, where possible. And ultimately, having those methods helps add different use cases to this. EVs and batteries are one piece. PV rooftop is potentially another that we're not looking at too closely yet, but we built it in a very modular network so that if we want to add that, it's not redoing a code base, it's adding a module. So we plan to work with BRPL to hopefully come up with some good ideas on investment decisions to take to their regulators so they can start to think about these issues more. So thank you. And Akshay is the one you should email, although you can also email me if you have any questions about this. So thank you.